Good afternoon, everyone. So the topic today here is it's a workshop talk, but for today it's an introduction to power and sample size calculation. And so before I get started, when we say that this is supposed to be kind of practical talk, I'm going to walk through some details of how you can actually free software programs carry out some different examples of basic power and sample size calculations. And as I was just saying, maybe the most ideal setting for this would be a computer lab where we actually hands-on. We unfortunately don't have that here today, but we have so I have these slides. They're going to have a bunch. You'll see a screenshot if anything is at all small, difficult to see from the audience. I do apologize, but I know that these slides are all going to be put online, and so I think that if there are things that you are interested in here that you want to go back and look at and download the program and work through and try out yourself, then what you could definitely do is obtain a copy of this online when the slides are posted, and you could actually use it for that purpose and work through the examples that I'm going to demonstrate here today. Okay, so let's see. So we're doing an introduction to power and sample size calculations here. We'll start out just for those who aren't familiar. What are we talking about when we're saying calculating power? What does that mean? It's not power like an electrical outlet. We're talking about power to detect associations or effects in research studies where you're doing statistical tests of hypotheses. So when you're applying a statistical test of a hypothesis, our null hypothesis is H0, and that's what we perform a statistical test to either reject the null hypothesis. We'll reject the null hypothesis if our statistical test tells us that the data that we observe is very unlikely, typically 5% or less, to be observed just purely by chance. In that case, we would reject our null hypothesis, or the other finding might be that we fail to reject our null hypothesis. And so the diagram up here is showing the kind of 4 different options that may turn out. There's some kind of underlying truth. There's either that null hypothesis is actually true or that null hypothesis is actually false. And then we're going to have our study findings based on the statistical test of that hypothesis. So, there are 2 different cases in which we get the correct result. That's either if the null hypothesis is true and we fail to reject it, or if the null hypothesis is false and do reject it. And then there's the 2 cases where we make an error, get the wrong result, and those we call type 1 error, which is a false positive result. The false positive result is what we will call alpha. We often, if we're calculating p-values and you say p is less than 0.05, 0.05 is the alpha. That's the false positive. Probability of a false positive result. And then we have type 2 error, which is labeled beta, that's the probability of getting a false negative result. So that's what if your null hypothesis is actually false, but you failed to reject it. Okay, so power is when we get the power is of the study is in the case that our null hypothesis is false. So we want to reject that null hypothesis, and we actually do reject it. That's power, and that is in this kind of 2x2 table. That's 1 minus beta. It's the probability, 100% probability minus the probability of having that type 2 error. So this is what this is power. That's the kind of quantity we're calculating. It's how probable it is that our study would find the correct results in the event that our null hypothesis is actually false. And so here's just another way of looking at it kind of graphically. If we're thinking that, and we have two we have two distributions here. We have the red and the blue, and so we're comparing. We're getting those represent say two population groups that we're comparing, and the parameters. So say it's a mean value for population red, the red population that we're testing, the blue population that we're testing. So for the red population, we're gonna obtain a measurement somewhere within that red curve. For the blue population, we're going to obtain another estimate somewhere within that blue curve, and then we'll compare them with a statistical test. You can see that green line representing the cutoff value, the critical value for the statistical test. If it falls, so if our observation from the blue population there falls into that little blue shaded section labeled beta, well, that's our type 2 error. That's where we've fallen on kind of the wrong side of that critical value test line. We have failed to reject the null hypothesis and we a type 2 error. If we fall into the other section of the blue curve that represents the power, make the correct conclusion. And what you notice in this particular example is that there's little overlap there. So this would be an example where we have high power. That's good. So that's that's the kind of power you hope your study has. So that's what we're going to be talking about calculating. Now, when we talk about power calculations, we're actually talking about estimating one of three related parameters. So there's power, which we just talked about. That's very closely related and dependent on the sample size and the detectable effect size. So we have these three quantities, and in any case, when we can estimate one of them, and we'll need to make assumptions or have information about the other two, and collectively we call the power calculation. So the calculation may actually be for power, or it may be for sample size, it may be for the detectable effect. Okay, so what are some of the reasons that we would want to conduct power calculation? So it's important for study planning. If you're planning a study and you're making decisions about how you're going to do that, how many subjects are going to be required for your study to statistically detect hypothesize effects. It can, it's going to inform cost in terms of the power trade-off between selecting your target sample size and costs, money, resources, time, participant effort in order to have a bigger sample size. But if you, what you want to have, so you don't want to kind of not uselessly do that, but you want to have enough power to find something. You don't want to just do your study and then say, well, I didn't find anything, but it's actually because I just didn't have enough people to actually tell the difference between my groups. And then if sometimes you already know the sample size, maybe you have 100 people and that's it, and that's the max have. Well, is the effect size that you are possibly going to detect by doing a study an effect size that's going to be meaningful, or is it not going to be meaningful, or is it not reasonable? And then you may want to consider, should I do the study and show them for maybe a different population. So it's typically an element that's required in applying for funding for any study to ensure good use of money and time and effort in terms of resources and also ethical consideration if you ask the participants to do something for a study in terms of making sure that kind of use of their time or giving some study that they're giving blood or it's kind of or something that could potentially result in findings that are important for health. And then also if you have a study that has null findings, studies where someone did not reject the null hypothesis, just for evaluation purposes to kind of figure out retrospectively, is that maybe that's really because there's no association between the risk factor and the disease they're looking at, or is it because they just needed to do a bigger study to be able to learn that? So there's various different kinds of software that can be used for power calculations, and there's a whole world of power calculations that are much more complex and get into all kinds of detailed situations that are not going to be discussed today. This is just an introduction here, but some of the free software available are programs called G-Power, PS, which stands for Power and Sample Size, a program called Power. The program R, which is free, has many different functions, and new packages are written all of the time. And then there are also options available in software that you have to purchase or have an annual license for, such as SAS, Data, PASS is a specific sample size program. Let me see. So the one that I'm going to demonstrate today is the G-Power program. And so the reasons, some of the reasons that I've picked this one are that it's free, it's available for Windows or Mac. You can just go, I have the website here, you can go there, download it, set it up, install it. It's easy, and then it's easy to use a graphical user interface that you'll see. I'll have a bunch of screenshots. It has a drop down menu, so you don't have to learn any special coding or no coding for something as you do for some statistical packages. It has a pretty good variety of statistical tests and functions available, I think, compared to some of the other packages. And also personally, I tend to favorite and use it a lot for the things that it can do. So it's natural that I would kind of share that. So this website, as I mentioned, you can download and install the most recent versions of this program, and you can also find there the reference manual. They have some tutorials there and published references that if you want to cite program. Okay, so now most of what I'm going to do is walk through different examples of some scenarios to illustrate how we use the G-Power program to conduct several different basic types of power analysis. Or when I say power, I refer to power and detectable effect size. So in going through these examples, we'll also demonstrate some different issues related to factors that will impact the power of a study, and look at, through doing the calculations, learn a little bit about what the increase or decrease of power. There, as I said, there's many different scenarios and options that are not going to be covered, but I hope this will be a basic introduction to get you started with this tool. And then just note, I'm going to kind of give some different examples, and I might, but they're just to let you know, they're all hypothetical, and they're kind of to reflect themes of the conference, but they're not. None of these examples are from actual data. Okay, so here we have example one. Example one, we have a cohort study that's comparing outcomes between two groups, an exposed and an unexposed group. So exposed and unexposed is the dichotomous variable, and here we'll say it's a childhood trauma exposure. So we had a group that was exposed to childhood trauma, a group that did not have that exposure. And we have a total study size of 1,000, and 450 of those are in the exposed group. So now we want to test whether the prevalence of several different mental health outcomes differ between the trauma exposed and the trauma non-exposed groups. So the outcomes that we're interested in are past year depression, past year suicide attempt, and a lifetime major depressive episode. And for this source population from which the study is drawn, I have the prevalence of each of those conditions of 10%, 1%, and 25%. And so, you know, the hypothetical example is like, this would be information I have from, you know, maybe from a local health department or national, on the prevalence of some of the disorders, and we have some information about a study that maybe this is an existing cohort or population that we know about that we can include. So here, we're going to test whether the prevalence of the outcomes differ between two different groups. So here I have the screenshot. You see, oh yeah, okay, I can use this for pointing as well. Okay, so when you open the program, you'll see this, you know, the window opens up, and here I'm selecting tests, and then we're saying these menus drop down to select our scenarios. So we have two separate groups. So that's the two independent groups here, and prevalence is a proportion. We're comparing proportions between the groups. So we selected proportion, and then we have selected two independent groups. Independent is because they're separate. We didn't like match them. There was nothing in the information that we matched the exposed to the unexposed. We just happened, you know, some people happen to be exposed to unexposed. So they're considered independent. Okay, so then, you know, after putting in selection, the window will look kind of like this. We see the proportions inequality to independent groups. So the test that we had selected, and now we're going to choose here where it says the type of power analysis. The type of power analysis section is where we can pick between basically the power sample size for the detectable effect size. Now here we already have a set sample size, and we do not know the effect size. So we are going to specify a power that we want to have, and then we're going to calculate the effect size, which our study will be able to have. Okay, so now we're going to fill. We've made that selection. Some computer required effect size. And so now we have to fill in down here below, or actually on this side, the input on the input parameter side, the details related to our study. And so some of those are starting with we'll always have the option to select the 2 or 1 tailed test. And we should select the 2 tailed test unless we are already certain about which group is going to have a greater prevalence, or you know, or which group has the greater value than the other, which direction it's in. And then if we do a 1 tailed test, we're only testing a hypothesis in one direction. you know, typically we may have an idea, but a two-tailed test is going to be more conservative. Okay, so here next I'll tell you about this alpha error probability. That's our alpha rate from the 2x2 table. That's our it's usually set at 0.05. That's the traditional type 1 error rate, and so we'll use that. And then here we can fill in the power that we want. 80. So usually you want to choose at least 80% or higher. 80% is often is common. So we'll set the power for 80%. Okay, here we have some of those. We keep filling in the details. Here we have to fill in this proportion. The proportion who are affected with the outcome in the comparison group. So we said that we'll look at depression, vascular depression first. We said 10% of the general population has vascular depression. So that's what we expect for our unexposed group. That's a good assumption. So we'll fill in 0.1, which is 10%. And then here we have to specify the effect direction. Now, we hypothesized that the exposed group has a higher outcome prevalence. Here for the proportion in the unexposed, we call the unexposed is P2. So P1 is our exposed group. So we say we choose P1 greater than P2. If we wanted to hypothesize a protective effect, we could set it the other way with the drop down. And then finally, for the sample sizes, we said that we said the exposed group was group P1. So we put 450, which was the number in the exposed group in the sample size for group 1, and 550 is the we said 1,000 total, so 550 are the unexposed group size in sample size groups. Okay, we will hit calculate to see the results. Okay, and so up here we see this proportion P1. This is 0.159, etc. That's 15.9%. So we can conclude here that assuming an alpha type 1 error rate of 0.05, an exposed group of 450, a comparison group of 550, and a 10% prevalence of depression in the unexposed group, we will have 80% power to detect a difference between groups if the prevalence in the exposed is 15.9%. So the proportion that we've gotten here is 15.9%, and that in comparison to the 10% that we said in the unexposed. So that's kind of the level of effect that we're looking at being able to detect with this hypothetical study is, if the exposed group has at least 15.9%, almost 16% prevalence of depression in that group, we'd be able to statistically detect that. Okay, so here I wanted to show you that there we just calculated what is the prevalence of outcome in the exposed group that we could detect this difference. But maybe instead of calculating that prevalence, we want to calculate a different quantity. Maybe we want to think in terms of we could either calculate a risk difference or a risk ratio between the exposed and unexposed group. And so to do that, we can use this option button that will be at the bottom of the screen. We could hit that button and this pop-up box shows up. And then here we could, for example, say if we're interested in a risk difference, we can choose the difference here. So that that P1 minus P2 should be the difference in prevalence between the exposed and unexposed groups. So we could keep all of the input parameters the same after we changed our request to difference instead of the prevalent, and calculate, and then we see here now that instead of 0.159 we have 0.059, and that's because we calculated, instead of the prevalence in one group, we calculated the difference between those groups, and that is roughly 6%. And you can see that if we calculate it all out, 15.9% minus 10% is the 5.9 that we see here. Okay, and then, so let's see. So now, continuing on with the same example where we've been testing whether the prevalence of outcome differs between two different groups, the exposed and the unexposed groups. But remember that we were saying at the beginning, we were actually interested in a few different, in testing a few different possible outcomes. So we just looked at one where we were assuming it was about 10% prevalence. But now we're also interested in more rare outcomes that's only 1% prevalence, and a more common outcome that's 25% prevalent. So we could see what would happen in those scenarios by changing this proportion P2, the proportion in the unexposed group. So if we enter 0.01 for 1% there, we'll see here this is the risk difference, again, that we were just looking at, where in our first example, which was about 6%, we see that for 1%, a rare, much more rare outcome, we're down to 2.5%. And for a more common outcome, we have about 8% there. Okay, and so here, yeah.
I don't know if all of us are familiar with statistics, right? But in this case, that the p-value is not statistically significant. So what do we do in this change? Will we have to change the powers and increase the power to have solve more simulation until we get this 7%? Of course,
well, so here the example that we're calculating, remember, is we have actually set our alpha. So we're saying we're assuming this is, so we're saying this would be the 0.05 level. What we're calculating is the risk difference that we could detect, but it is the question, because like we said, say for the first example where we said, okay, for that depression that was 10% prevalent in the typical population, we calculated we could detect a risk difference of 6% for a 16% prevalence in the exposed group. What if we say, maybe we have a lot of piloting, maybe we have some more information, we actually say like, well, based on what people have seen, we think the depression is higher, but it's more like 13%. And maybe, in that case, we're not going to be able to detect that difference, because maybe like we think there is a difference, but it's only 3%, it's not 6%. If you have enough information to say that, then then in that case we say, okay, the study's not going to have it. We can't, instead of we won't have 80% power to detect that, and then you might want to change something about your study. Or you might say, well, that's not an outcome that we should look at in this study, and we should focus on putting our energy into assessing a different outcome.
No, but in this case, because we are not calculating power, right? Because the power is of the data, we select 80%. And as it is a cohort studies, that anyone will have the sample size. So in this case, can we, by example, instead of using 80%, we use 85%, 90%?
Yeah, and we will do that at some point along, but that you absolutely, if you want to have more power, if they want to do more, sure, you can vary that. Okay, and so here's an example of kind of what we can do. As we're talking about, you can vary these different things, the different parameters, and okay, yeah, and what I like to do is use some different scenarios, vary some different factors, and then put the results together in a table, and that's a way that you can organize kind of your information to help you make some decisions about your study or present scenarios, say for a funding application. And so here, I've filled this out with, we see here the different outcomes in the prevalence, which we talked about 1%, 10%, and 25%. And then actually, we talked about different ways that we can present this. You can look at it, say, here's the risk difference that we were just talking about. So that's the 5.9% in the depression group, and then for the 2.5% and as high as 8%, depending on our outcome prevalence in the unexposed. And what you can note here is the way I kind of filled out this table is I started with that, and then also used these other factors that we could calculate. What would that mean about the prevalence in the unexposed? I mean, in the exposed group, what would that be? And this, this value here, this prevalence in the exposed group, might be really what you would kind of practically be looking at if you had some pilot data or some information, saying, is this, if we're looking at this 25%, this outcome, is the 33% reasonable? Is that something that might be what the exposed population is experiencing? We could also think about the risk instead of the difference between the two groups, a ratio between the two groups. So I also have those here, and what's interesting here, or just like something to note, is that actually, although, if we're looking from the least prevalent outcome to the most prevalent outcome, the risk differences that we can detect actually kind of mirror that. The smaller risk difference can be detected for a lower prevalence outcome. But the risk ratio, when you look at a ratio measure instead of a difference measure, it's actually reversed. So the risk ratio, it's actually, you can, for the low prevalence outcome, you can only detect a pretty, relatively high risk ratio. And that's the smaller risk ratio can be detected for a higher prevalence outcome. Okay, so let's go to the next example. We're going to compare a continuous, and we'll say a normally distributed or roughly normally distributed continuous outcome between two different groups. Okay, so we're going to stick with some element. We're going to stick with our same cohort study. We're comparing an exposed and unexposed group. They 1,000 total, and 450 were those who were exposed to a child. Now we are interested in the long-term physiological impacts of trauma, and so we want to compare a biomarker, which is a normal, which happens to be in this theoretical example, normally distributed between the two groups, and see if that differs. Okay, so but this now relies on an expensive lab test. So we would like to do this testing on a smaller, randomly selected subset of the cohort because we have to have funds for this. So which parameter do you think we should estimate in this for this? Anyone want to hazard a guess? No guesses? The total, you can choose power, sample size, or detectable effect size. And we're trying to plan our study. We're saying we want to choose how many samples to test. Sample size. Okay, so now we're going to do Okay, sample size for comparing. The outcome, let's see, so now we're gonna compare mean, you said you want to compare means, so we've selected means. And we have two independent groups, just like, you know, the same, since we're on the same scenario, that we've got two independent groups. Okay, so after selecting our test, we have to choose the type of power analysis. And this time we're picking sample size. So, let's see, so this is, so here's our screen. Again, we're gonna fill in the input parameters. So here for the alpha and the power, we've selected 5% and 80%, again here. Okay, so here, this, we have to fill in the allocation ratio, N2 over N1. This is the ratio of the sample sizes that we are going to include from the exposed and unexposed groups. So here we're going to say, remember we had 450 exposed and 550 unexposed. We're going to say, let's keep that same ratio. So we just calculate what does, you know, what's 450 divided by 550, we get 0.82, and we fill that in. So we say, like, let's keep the ratio for our study the same as the overall study ratio. But here I also note that we could choose, we're selecting a subset, so as long as we have enough participants, we could also choose that in a different way, where, you know, such as 1-to-1, you know, in which case, you know, just calculate the ratio and fill in the alternative. Okay, and then here, we're calculating sample size here. So when you're calculating sample size, remember, you always have to fill in two of these three parameters. So we filled in the power, we selected 80%. We also need to select an effect size here. And sometimes we might have information that will help us decide exactly what to fill in. Sometimes we don't. And so here we'll say, okay, we don't really know, but we can use the effect size convention. This little dialogue within effect size convention to kind of help guide you here if you're not sure what to fill in. This kind of pops up when you're using the program. If you hover your arrow there, like, so this pops up and reminds you, okay, let's be conservative and say, if we want to be able to detect the small effect size, what should we do? So we fill in 0.2. Okay, we'll hit calculate to see the result over here on the output parameters. And then here we get the information about the sample sizes, and we conclude that assuming alpha of 0.05, the allocation ratio of 0.82 between the two groups, the sample size that will be required to detect a small effect size at 80% power is going to be the total of 796. And then it also gives you the distribution for your two groups, which should be what should be the total sample size for each of those two groups to get that. Okay, so here, and now remember I was saying that for that effect size, if you know, if we have a little more information about the possible outcomes for the biomarker measure or the possible distribution for values for that biomarker measure, and instead of just making using kind of a default assumption, we can be a little more precise about our effect size C that we fill in. So you can do that by selecting this determine box, and then you'll this dialog would pop up, and what one would have to enter in this dialog box is information about the expected mean and standard deviation of your continuous measure for your two different groups. So here you're saying for the mean for group 1 and 2 and the standard deviation. So it's going to be a situation where you'll have to have some, you know, some information from the pilot study or from other studies that people have done where you might, be able to fill in values. Okay, and so one other possible variation here is that, remember I had said we were assuming we were looking at a biomarker measure there that was normally distributed or pretty, roughly normally distributed. Okay, what if it's not? If it's not, well, one thing is you might do a transformation, like we often do a log transform of biomarker measures, and that gives us a much more normal distribution, and then we can just use the log. But if not, we might want to do a non-parametric test. So here we again pick means that we're comparing, and here we could do two independent groups, but we're choosing a non-parametric test. We go on the input parameter side, we fill in similar assumptions again to those that we just used for the normally distributed outcome. And then we hit calculate and get our results here on the output side. So you can remember, you may not remember, but I'll remind you from the screen before for our parametric strategy. The required sample size at 80% power was a total of 796. We see here that for the non-parametric test, the required sample size at 80% power is going to be 834. So you see that in that case, we would actually need a little bit larger sample size to have the same power. And so what that is showing you there is that when you are able to use a parametric test, which means you're assuming something about the distribution, and that we're like, if we can assume that we have a normal distribution of our outcomes, we can get away with a little bit smaller of a sample size and still retain the same power. So that's an advantage if we can do that in terms of simple tests. Let me see. Okay, so now we'll talk about an example. Here we have a case control study with a normally distributed exposure. Okay, so let me see. So this hypothetical case control study is, we'll say, suicide attempts, cases, and population control were when we see doing a case control study here. We have a thankfully rare outcome, in which case a case control study is a good design. So we're going to say that we expect that we'll be able to have enrolled 100 cases and 200 controls. And we're going to test our hypotheses using logistic regression, which is an appropriate method for analyzing these control studies. So here, let's say we're looking at a psychological scale measure of exposure. For example, well, this is a real example, but it's not magic. It's like a real histogram of the intolerance of uncertainty scale data, but it's not from this. It's from a different population. But we'll say that it looks reasonably normally distributed here, and we have a mean of 34 and a standard deviation of about 10. So here we've okay, so we'll have our screen pulled up again. This is so here I'm just showing, instead of we can do all of this drop down menu that's cut off, we can select our statistical test either using that drop down menu or by using this test family and statistical test, these two boxes. So in this case, I'm showing this way. I chose logistic regression, which is under the Z test, the test family box. That's the statistical test we select. here, the effect direction, again, we have to specify that, and we're going to be computing odds ratios. We want to hypothesize an odds ratio above 1. So we're looking at an odds ratio in terms of risk factor, something that increases risk. So we're selecting P2 is greater than P1. If we wanted to look for a protective factor, we select the other direction. So here, here the probability of y equals 1 given x equals 1 in the null hypothesis is going to be the prevalence of our outcome in the sample. Remember, we had 100 cases out of 300 total participants. That's 100 cases, 200 controls. So we have 100 out of 300 total. It's 0.33. So we fill 0.33 there, and our total sample size is 300. We fill in there. I don't have the arrows to keep things a little cleaner, but we've also specified alpha equals 0.05 and the power of 80%, just kind of keeping that the same as before.
Sorry, this is a question.
Mm-hmm.
This is only case 1, right?
Mm-hmm.
And but why using prevalence?
Why are you using what?
Prevalence. What's normal calculate prevalence?
Prevalence?
Yeah.
Well, this is the it's the prevalence in our sample. So how many, we have to let know how many cases. Like,
Yeah, no, what I mean is that as we take case control, remember that we have a number of cases that we have in the selected controls. So that means there's on the requirement that the assumption that the case control study we cannot calculate prevalence.
right.
Right, so that's my question. So why we have to use prevalence in this case? Because we cannot calculate prevalence in case control.
Yeah, no, it's not, what I'm putting in here, this 0.33, like, that's not the prevalence of the outcome in the overall population, right? This is, because it's the, yeah, it's the prevalence of the outcome among your study subjects, cases, plus controls. So it's like a little bit weird of the way, you know, I think this, and this is why, you know, I think this is like, it's helpful just walking through, like, you know, how to figure out what entry to make in each of these, you know, cells to kind of do the calculation. So, you know, the lead one, I think the okay, so let's see, the other things we have to fill in here. We have this cell R squared other, you know, labeled R squared other X. This refers to inclusion of other covariates in the model. We're doing a logistic regression model here. So if we're including any other covariates besides our main exposure of interest, we can account for that using this cell. Right now, we're going to set it to 0, and that means right now in this example, we're not considering other covariates. We're just considering our main exposure. And then down here, we can enter some information about that X, that main exposure. So we pick a normal distribution, and then here we're actually going to choose, we're just going to choose 0 for the mean and 1 for the standard deviation, instead of entering specific values. And what that will do is it will let us calculate a detectable odds ratio for a 1 standard deviation change in X, whatever the standard deviation of X is. So in this case, that would be about, you know, the standard deviation was close to 10. So this will give a odds ratio for a 10-unit change in X. So we can hit calculate and see the results here. Here's our result, and from this we can conclude that assuming of our alpha equals 0.05, we have 100 cases and controls, a normally distributed exposure value variable, and no other covariates in the model, then we will have 80% power to detect an odds ratio of 1.42 for a 1 standard deviation increase in the exposure. And here I'm saying, remember that means for about a 9.9 or just about 10-point increase in one's score on this scale.
So it's here. I thought, of course, most of the time we are interested in when they are interested in the hypothesis, right? Because even though we can be sure, because what is significant. So in this case, we have to use, like, the critical C and check if they able to see whether it's significant or not, or because use that classical.
Well, this is saying that if we had, if we had the scenario described in terms of the population or exposure, et cetera, that if the if the true odds ratio in the exposed versus unexposed is 1.42 or higher, then we should get a statistically significant p-value when we do the logistic regression. So, is that reasonable? It's again something, maybe you could look at some, if you don't have like pilot information or even something, pilot information sometimes if it's small, it's not, but maybe something from the literature, if other people, people in another country have looked at this exposure and outcome, maybe there's some other studies you're saying, I was inspired by some other studies I've read and I want to see if we see the same thing in my population. You might look at what odds ratios they reported and say, are they reporting odds ratios like this big or small, or does that help? Well, I mean, in the in the scenario I'm describing, I guess, like hypothetically, we haven't done the study yet, so it's a prospective calculation. But you can calculate it retrospectively if you have the information and want to enter it. Okay, so now we're gonna use this example. Let me see. Okay, so we're using the same example. Okay, so this is exactly like what your question was perfect, and about thinking, like I was saying, maybe you'll look at some other studies and see what people have done. So say you do that, you go into the literature and say like, okay, is 1.42 for an odds ratio something that I think I'll attack. So you go and look up some studies and you see that people have reported significant effects, but they are actually reporting lower odds, lower than 1.4 in general. So you say like, okay, it's a good study idea, but I think that the true effect size is smaller. So I might need a different sample size. What kind of sample size would actually be required to detect smaller odds ratios? So I could do something right here in the G-Power program using this button XY plot for a range of values. And hit that, and this kind of a dialog box pops up. And so I make some entries here. I decide to keep the odds ratio on the x-axis, and on the y-axis put the total sample size. So I can look at different odds ratios and see what sample size I'll need. And then here, I just say, let's look at the odds ratio. It's odds ratios from, we'll say, let's go as low as 1.1. We'll go up to 1.5, a little higher than we had calculated before. And it gives steps here 0.05, so I can get some different values there. I have my power and alpha filled in and just check off some, values for the plot. I hit what button wasn't there, draw plot. we hit that drop off button. Oh, yes, and then we can see the results. And so here we see the different odds ratios, what sample sizes I need. So if I want to be able to detect an odds ratio of 1.3, we'll need a total of 530 subjects. If we want to detect an odds ratio of 1.2, so there you're going to need over 1,000 subjects. So it gives you some kind of idea of what you would need in this scenario. And do note that these calculations, we assumed that we were keeping that same 1-to-2 ratio of cases and controls. Another thing can vary. You can sometimes in a case control study help yourself out with power by increasing that ratio, getting more controls. That's so that's not shown in this scenario, but that's like if you were really in this situation, think about that and do some calculations that way. Okay, those are points of interest. Okay, so here we could also add a second line to the plot. For example, if we want to, instead of just having 80% power, what if we want to have, see what we would need to have 95% power, really good power there. We can, there's a section here we can fill in plot 2 graphs, and here we select with power, we'll say from 0.8, that's our 80% power, and then I just said in steps of 15%, so that will give us one other line with the power of 95% is 8 plus 15. And so you'll notice that for 95% power, of course, we'll need even larger sample sizes at a given observation. Okay, let's see. So now what about a case control study with dichotomous exposure variable? So here we're kind of using the same test and effect size calculation. Let's keep most of the assumptions the same. So say we're going back and saying like the same, let's think about the same hypothetical case control study. But here, let's think about what if we wanted to look at dichotomous exposure variable. So we pick binomial for the X distribution. That's for yes, no, dichotomous variable. And we'll say the prevalence of that exposure is 20%. So we put in 0.2. We'll hit calculate to see the result there. And here we see that assuming same thing, alpha 0.05, 100 cases, 200 controls. Here a dichotomous exposure variable with a 20% prevalence, and also no covariance in the model. Here we'll have an 80% power to detect an odds ratio of 2.28 for exposed versus unexposed. So here, you see going to the dichotomous variable, we're actually going to, if we're going to look at this, it has to be something that we expect is going to be pretty strongly associated with our outcome. Okay, so now one thing we didn't get into was the other covariance in the model. So remember we talked about that a little bit, this R squared for other X's, and I had just filled that in 0 and said we'll assume nothing there. Like, let's look at this example and see what happens if we say we want to consider, we are measuring some other covariates and we're going to consider them. So here we are keeping the same details, except instead of 0, we're putting in 0.1. And putting in that 0.1 means that we expect that about 10% of the variance in the outcome is going to be explained by whatever other covariates we're putting in the model. So you don't specify in terms of, you don't have to say, I'm going to have 10 versus 2 versus 20 covariates. It's not the number of different covariates that matters, it's how much of the variance in that outcome they're explaining. So if we assume 10% there, then we calculate this odds ratio of about 3.9, close to 2.4. If we assume 20% for the other X's, then the odds ratio goes up about 2.5. So you can see that what's happening here is when you're including covariates that explain increasing proportions of the variance in the outcome, you're going to have higher minimum detectable odds ratios for your exposure outcome of interest. Now, I don't know, I hope no one is taking this to looking at that and saying, wow, I should never, let me just like forget about ever including covariates in the model. That's going to mess things up. So, I mean, that that's not the right answer because unfortunately, I don't know, unfortunately or fortunately, or that including some different covariates in your model is often going to be important to address confounding. And so, what's going on when you can detect that smaller odds ratio as you're actually detecting something that's not really due to your exposure if you're not addressing those covariates, but you can see how that impacts the power. Okay, so let's see, let's stick with a case control study here for this example. And this is a different case control study here, where we have motor vehicle injuries for cases and population controls. And here we're going to say we have 200 of each, 200 cases and 200 controls. So we'll test again our hypotheses using logistic regression. And here we'll say that we have.
Sorry, if I will go remove this example here. On the previous example, when you were presenting curve with different power and the sample size that we supposed to use. Is this valid for the both cases and control or just for the number of control?
The numbers in the graph.
In the graph.
Yeah, here, why don't we just go back and look for a moment?
Yes.
So this was actually the total sample size. These were the totals. And so, for instance, let me see if I can find one of the. It's a little covered up here. I was gonna say the one around 1.4. You can see that like oh, okay. What I wanted to. Trying to see if we can look at.
What I would advise, guys, that
Yeah.
as you know that what we do is control, we don't have a sample size of cases because we already have the cases and then we have to go after the control. So the sample size of is just for the control, so that is why complicated is whether this is valid for both cases and control or just for the controls.
Well, I mean, you're calculating the sample size for the, I'm sorry, maybe we could come back and look through it after, look through it at the end. I was trying to find the where we have the breakdown of the cases and controls, because this is actually the total, and you're calculating in the different scenarios. They're not putting in your we put in our original scenario the numbers that we have based on cases and controls, but then when we calculated these are total sample sizes, and it's assuming that total is distributed 1/3 cases and 2/3 controls. But so it's like if you want to have this bigger sample size, you have to find more cases, like in this scenario.
No, yes, it's true, but the problem is that we have in this study, they're very aware. Let's say like something like hemophilia, and let's say that we have only 50 cases here and there. So that means even though we come with, this is 550 and you say 1/3. But we know that we are not going to reach this number of cases because we don't have those all the cases. But if we only have 50, this is only the people we have. So that means, let's say that I'm going to use one control for one case, or two control for one case, or three control for one case, but the number of cases, we already have the cases.
So in that case, you may want to do, I think, I was showing you this function where you can kind of graph it automatically, and I think for that scenario, you're gonna have to kind of do it by hand. Changing your total and your ratio and just, going through each of those scenarios and making your you can make a table yourself, like I was showing, you could set up the table, but you could make those assumptions, and that would be the thing to do there, but you couldn't use, this wouldn't handle it, with the options that you have. So, it's built into the program, it does some things you have to kind of do yourself. Let me just try to get through here so we just cover everything, but the questions are great. So here we are looking at 200 cases and 200 controls, and we're saying like we have some other covariates, and they're going to explain about 10% of the variance in the outcome. We know we need to include those, so assume that we are considering collecting information on several different hypothesized risk factors. And so the risk factors we're thinking of have prevalence of 1%, 5%, 10%, 25%, 40% in the population. So we have a bunch, they're all different kind of prevalences in the population, but although they're different prevalences, each of them are thought, are thought to roughly double the odds of the outcome. So we have some information to say each of those might be associated with about a 2.0 odds ratio, and we want to decide which of those risk factors should we collect. Any ideas about which parameter we should estimate? So this time we're going to go for power. So we have the number of cases and controls already, and we have the odds ratio that we want to detect, which is 2.0. So we'll calculate what power do we have. So this time we're again sticking with logistic regression, and for our type of power analysis, we'll pick power. Okay, so here our total sample size is 400. That's the 200 cases plus 200 controls. Here, 50% of the subjects have the outcome. And recall, this is 50% of the cases in our study. It's not 50% of all people in the population. And here for the odds ratio, the inputs are slightly different because we're calculating power. So odds ratio is an input here. We'll put in 2.0 because we have prior information to suggest that's what we want for the text. And here for the X, we are, we'll say it's binomial because we have dichotomous exposures. And so let's look at the one that's 1% prevalence first. And we also specify the alpha 0.05 and the 10% for the other acids. Okay, yeah. So and two tails. Okay, so here we can calculate and we see the results. So assuming our alpha equals 0.05, the 200 cases and controls and our dichotomous exposure variable with a 1% prevalence, with those other covariates explaining 10% of the variance in the outcome. Our power to detect an odds ratio of 2.0 in the exposed versus the unexposed here is going to be 8.3%. Okay, so that's not too encouraging. And look at this graph. Remember what I showed you at the beginning of the talk, those nicely separated graphs with that here, with that power. Well, here, like if you can see where my arrow is, that's the power for this scenario, okay, so, that's not looking so good. Oh dear, it's not off. Okay. Okay, so I reversed the animation here, but, we have, I think it'll work. We have several other exposures. Remember, we were interested in a kind of list of them. So let's check them out one by one. The one 5% prevalence. You see our power here, that's 26%. Here we have the 10% prevalence exposure. Okay, our power is up to 46% there. Our 25% prevalence exposure. Okay, our power is up to 78.5. And then for the 50%, whoops, for the 50% prevalence exposure, now we're up to 89% power. And so we could take all of that information, you know, and so this is what I'm saying for sometimes we kind of have to put everything in and just do it separately one by one and then put together a table of your results. So here we've lined up our results and we have for each exposure prevalence and we label our table stating our other assumptions. What is our power to detect an odds ratio of 2.0? You know, we see that increases with the higher exposure prevalence, higher prevalence exposures. And so for which exposures would we conclude that we have what we say adequate power? Any ideas? 50%, yeah. Yeah, so I mean, usually you want to have at least 80% power. So, you know, you might look at the 25% one is close. So maybe if we went, oh, you know, and you could keep filling in, you know, maybe we find out if we said like 28% or something, we'd get there. Yeah, or the in the unexposed, or you know, or you can often just use like if you have general population data, you could use that to estimate. Okay. Oh wait. So just yeah, and I'm just about to wrap up. But what could we possibly do? If you know, one thing is if we were just making a decision and we're saying, okay, we can only measure one exposure, maybe like okay, we figured out which one we could do. What else could we try to do if we want to be able to measure some of our detect association for some of the other exposures? Any ideas? Well, you know, like one thing is probably increasing our sample size. So we have to see if we could actually make a better study. Okay, so let's see. So to wrap up, a summary of kind of the steps that we'll go through to do power calculations. So one, we're going to start by thinking about selecting the appropriate statistical test. Two, we're going to choose the type of power analysis, which parameter do we want to estimate, and so which ones are we going to assume. Next, we enter the assumptions for the required parameters. We calculate. Sometimes we'll go back and alter the assumptions if we need to test a different range of assumptions. Next, we can summarize our calculations in tables or graphs. And then finally report the results and including a statement of assumptions. And if you'll notice, like as I went through each time, I kind of would state over and over again, you kind of get of hearing alpha equals 0.05, but you always, it's kind of a part of reporting your power calculations that you always want to be clear about what were the assumptions, because as you've seen, you can change all of those assumptions and you get different results. So you always want to stating that as an important part of reporting